Hey, so we're on 2.10, using the rational root theorem to find real and imaginary roots. And the first 2 pages are kind of just an intro exploring, okay? And our goal or objective is to find all roots, real and imaginary, by applying the rational roots theorem, a polynomial function. Real roots, so real numbers, can be one of two types, either rational or irrational. And if you've forgotten, rational means can be expressed as a fraction. Okay, you know what is good for you guys is that we get rational roots from factoring or synthetic division, and we're going to get irrational roots from the quadratic formula, okay? Because it's like the irrational means it can't be expressed as a fraction, so it's going to be like your square root of 2, square root of 3, square root of 5, square root of funny numbers, okay? Non-perfect squares. So, ready? This is our exploring page. Consider this function whose graph is pictured below. It's a positive quartic, and we see it does look like a W. 1, 2, 3, 4, 1, 2, 3, 4 matches a quartic. Positive leading coefficient means it's going up. We have a y-intercept of 9, all right? What three things about this graph make sense after investigating the equation? I think I just said them all. So, what makes sense? Is that how you spell positive? No, that's how you spell possible. Positive leading coefficient. I think I misspelled this today, so I'm gonna spell it correctly. Yay, positive leading coefficient means both end behaviors are going up. So both arrows are going up. And you could have said as x goes to positive and negative infinity, f of x or h actually goes to positive infinity. So, or you can write it out as a sentence. So number 2, what's the other thing we found? The constant term is 9 and the y-intercept is 9. So constant term at the end equals 9, which is the y-intercept on the graph. Intercept. And what was the other thing I said? That it's a power of 4, it's a quartic, so it has 4 x-intercepts, which we're going to call roots. So quartic is showing us 4 roots. Awesome. What conclusion can you draw about the 4 roots of the function h of x? Explain your reasoning. What conclusion can we draw? Well, we know they're real numbers. They actually exist. This one's 3. This one, are these whole numbers or are they going to be fractions? So what conclusion can we draw? Well, since we see 4 x-intercepts, the 4 roots are real, as opposed to what's the opposite of real in math? The opposite of real is imaginary, right? So they're not imaginary, they're real. They're actually there. So since we see 4 x-intercepts, the 4 roots are real. And what else can we say? Let's see, these 2 are, what do we know about them? They're negative, right? With 2 negative and 2 positive. All right, lots of writing, but it's notes, right? I guess that's what notes are. The goal of this lesson is to use the rational root theorem to aid us in finding all the roots of the function, whether they be rational, irrational, or imaginary. That is loud. I'm going to have to pause. Pausing. Okay, so I paused and I wanted to make sure that you knew that rational and irrational are the real numbers. So these are real or imaginary. Next thing, make a list of the rational roots. Okay, a list of the rational roots. So some kids think that that means you make that table, but that it doesn't. So you need to make sure that you know that whenever it says make a list of the rational roots, you know what to do, that the rational root theorem guarantees are possible. Okay, and so what this means is this formula here. The factors of the constant divided by the factors of the leading coefficient. You ready? Okay, what was the constant? The constant was 9, so we're going to have plus or minus the factors of 9 over plus or minus the factors of the leading coefficient, which is 3. Okay, but we got to list them all out. It's not just 9 over 3. So what goes into 9? Well, we start with 1. 1, 2, no, 3, 4, 5, 6, 7, 8, 9. So it's just 1, 3, and 9. And then what are the factors of 3? It's prime, so it's 1 and 3. All right, here we go. 1 divided by 1 is 1. 1 divided by 3 is 1/3. 3 divided by, I said it right, but I wrote it wrong. 1 divided by 1 is 1. 1 divided by 3 is 1/3. Next, 3 divided by 1 is 3. 3 divided by 3 is the number 1, and we already put it. 9 divided by 1 is 9. 9 divided by 3 is 3, but we already have 3. Okay? All right. From this list, that's nice. That's a nice list, right? 1, 2, 3, 4. There's only 4 numbers, but they're positive and negative, so there's actually 8 possible, right? It's nice, small. From this list, which roots appear to be the roots from the graph above? Perform synthetic division to verify that they are in fact roots. Okay, you ready? Here we go. Do we see a positive 1 as a root? No. Do we see a negative 1 as a root? No. So we can cross off 1 and negative 1. We don't need it. Okay? What about positive 1/3? Is positive 1/3 a root? Nope. What about negative 1/3? Hey, that could be one of them. So let's write x equals negative 1/3. Okay, I think in my other video I circled or highlighted it, so that might be helpful. So we think that's one of them. We'll see. All right, what about positive 3? Is positive 3 a root? Yep, pretty much guarantees that that's one of them, right? Positive 3. So we have x equals negative 1/3, x equals 3. What about negative 3? Did negative 3 show up on the graph as a root? Nope. Okay, what about 9? Plus or minus 9? The graph doesn't even go out that far, and could it come back down and hit 9? No, it can't, because it's a quartic, and we already have our 1, 2, 3, 4. Ooh, I have a question for you. Does this 9 go with this 9? No, this is the y-intercept, and we're talking about roots, so that's the x-intercept. Okay, so no 9s. We only got 2. Did I miss one? What is that? Oh, interesting. Okay, well, let's just do what it tells us to do. Perform synthetic division to verify that they are in fact roots. Divide h by one of the associated factors. Okay, which one do you want to do first, my friends? Let's do the 3, right? The 3 will be easier than the fraction, so let's start with the 3. 3, negative 8. Are we missing a term? No missing terms. Okay, so we're going to do this. Skip a line, draw a line, bring down the first term, multiply and add remainder at the end. Negative 27 plus 24 would be negative 3. 3 times negative 3 is negative 9. And we have a 0. Yay, it's a factor. Okay, but you guys, don't do the negative 1/3 in the original again. What we just did, we divided h of x by one of the associated factors. Then divide that result by the other associated factor. So do you guys see here the depressed equation? I know, it's so sad. The depressed polynomial. We're going to divide the depressed one, not the original. Here we go. Skip a line, draw a line, bring down the first term. -1 times 3 is -3 divided by 3. -3 divided by 3 is -1. 0. Ooh, we like 0. 0 times a fraction is 0. -9. Okay. -1 times -9 is +9. +9 divided by 3 is +3, and we get 0. Friends, did we check that they're both factors? Woohoo! But there's that other one. That is so weird. Wait, and didn't we didn't see this one either. Oh my goodness. So we had a -1/3 and the +3, but these two are unknown. I wonder what they could be. We did everything for this part. You have just divided a degree 4 function twice. So your resulting polynomial, like what is this polynomial? What is this going to be? What's x to the 4 divided twice? We divided it by x to get an x cubed, and we divided that by x to get an x squared. So this is a quadratic. Does that make sense? Okay. Well, we already know that that's a constant, that's x, and that's our quadratic. Yeah, if I told you to write that polynomial, so right, watch. 3x squared plus 0x minus 9. That's how you would write it. Yes? Do we need the 0x? No. Okay, what do we do this? What do we do with this? This function's roots will be the remaining two roots, which will be, what word is this? Irrational. What did I tell you about that? Where are the irrational roots going to come from? Find these irrational roots. Where are they going to come from? Top of the page. From what? The quadratic formula. Okay. Now, normally we would have to use a quadratic formula, but we don't have to on this one. Set this equal to 0. Set equal to 0. It can't be factored. If it could be factored, we would have found the roots up here in the rational roots. So we would have to go to the quadratic formula, but actually because of this 0x here, we can solve it by taking square roots. Now, if we had any other number here, we'd have to go to the quadratic formula. So look out for those examples coming soon to a theater near you, where we're going to have to use the quadratic formula. But here, add 9, divide by 3, and we get 3. And what's the inverse of x squared? Square root, right? But what happens when we take a square root? We're going to have a positive answer and a negative answer. Okay? These are the other two roots. And because they're the square root of 3, I said that as an example, they are irrational. 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 Okay, let's look at the graph. So this was our root of 3. That's a rational number. This is our positive square root of 3. This we found was -1/3. And then this number here was our negative square root 3. Irrational, rational, irrational, rational. How did we get those irrationals again? We took our rational roots, we did synthetic division, and then we took this, and it's a quadratic, and we set it equal to 0. And then I said you have to use a quadratic formula, except in this case it was a little bit easier. Okay, to turn the page and pause the video. You could try this on your own or copy it. And then you're going to try D on your own. And then we'll begin E in class together, okay? But what this says is, what doesn't make sense? The degree is 4, but the graph only shows 2 roots. So we can see the two real roots, which means 2 must be imaginary. We can see 1 positive, 1 negative, 2 imaginary. Possible rational roots.